welcome to the deep dive. Today we're plunging into the really fascinating world of large language models, LLMs, specifically how they learn to reason. Our mission really is to figure out if the techniques we're using are genuinely teaching these models new ways to think, or maybe just making them better at finding answers they could have found anyway.
Exactly. And what's emerged is, well, it's quite the head scratcher, as you say. It looks like maybe they aren't learning fundamentally new reasoning, just getting more efficient at using what's already there.
Which had some pretty big implications, right, for where AI is headed.
Absolutely. We're focusing on this really interesting paper. It's from April 2025 called Does Reinforcement Learning Really Incentivize Reasoning Capacity in LLMs Beyond the Base Model?
Okay.
And it takes a critical look at reinforcement learning with verifiable rewards, RLVR. That's the technique many folks believe is, key to unlocking advanced reasoning.
Right. RLVR. Okay, let's unpack this a bit. So RLVR, in simple terms, it's like giving the LLM feedback, like rewards when it gets something right.
Spot on, especially for trickier stuff like math problems or coding challenges.
And the rewards aren't usually from a person clicking good job, right?
Yeah.
They're automated.
Yeah, often, like checking if the math answer matches the solution or if the code it wrote actually passes certain tests, that sort of thing.
Okay. And the common thinking, the belief, has been that this RLVR process helps the models self-improve, develop totally new reasoning skills.
Precisely. Skills like exploring different possibilities, maybe reflecting on its own steps, iterative refinement, that kind of advanced stuff.
And we've seen models that seem to do this, right? You hear names like OpenAI O1, DeepSeek R1.
Kimi 1.5, too. Yeah, these reasoning-focused models have done impressive things, and RLVR is often pointed to as a big reason why.
So the assumption is RLVR gives them a reasoning boost, pushing them beyond what they could do initially, like a superpower upgrade.
That's been the prevailing narrative, yes. But this paper, the one we're diving into, it really challenges that whole idea.
How do they challenge it? What's the method?
Well, they used a metric called pass at K. Now, this isn't just about getting the answer right first time.
Okay.
Pass at K looks at whether the model can solve the problem within K attempts. So if K is, say, 100 or 1,000, a large number.
Ah, okay. So it's not just, did you get it, but could you eventually get it if you kept trying?
Exactly. It gives us a much better picture of the outer limits, the actual boundary of the model's reasoning capability.
That feels important. Testing the true potential, not just the first guess.
It is, and this is where it gets really, really interesting. The findings. Honestly, quite surprising.
Go on.
While the RLVR trained models, the ones with the reward training, they did perform better with just a few attempts, a small K.
As you'd expect, right? They've been trained for it.
Right. But when the researchers allowed a lot more attempts, a really large K, the base models.
The ones without the RLVR training.
Yeah, the raw foundational models. They could often catch up and sometimes even outperform the RLVR trained ones.
Hold on. Seriously.
Yeah.
So the model that didn't get the specific reasoning training could, if you just let it keep guessing, sometimes do better.
It sounds completely counterintuitive, I know.
Yeah.
The paper uses a helpful analogy. Think of problem solving like exploring a giant search tree, right?
Yeah.
Lots of possible paths.
Okay.
The idea is that RLVR training makes the model really good at focusing on the paths it knows or strongly suspects lead to a correct answer. It becomes more efficient.
Like it's given a map highlighting the main roads to the treasure.
Exactly. Laser focused on those known good routes. But the base model, without that specific guidance,
It just wanders around more.
kind of, it might explore a much broader range of possibilities, even paths that seem less likely initially. It's like, someone just browsing randomly in a huge library versus someone using the card catalog.
The browser might take longer, but they might stumble onto something unexpected the catalog missed.
Precisely. The paper actually has a diagram, figure 1, showing this RLVR search is more focused, maybe narrower, while the base models is wider, more exploratory.
So the base model's potential success comes from just sheer breadth of exploration, eventually hitting the right answer.
That's what the findings suggest, yeah. And they didn't just test this on one thing. They ran experiments across a whole bunch of different reasoning tasks to see if the pattern held.
Like what?
Well, in math, they used everything from grade school problems like the GSM-8T benchmark up to really tough competition math, Olympiad level, AM problems, also Math 500.
Wow, okay. Across different models, too.
Yep. They tested this on different LLM families, Llama 3.1, Quen 2.5.
And did they see the same thing? RLVR models good at the start, but base models catching up or overtaking with more attempts with larger K.
pretty much across the board. Figure 2 in the paper shows these pass-at-K curves for the math tests. You can literally see the base model's line, often climbing steeper as set gets bigger, eventually meeting or even surpassing the RLVR model.
That's wild. Did it hold true for other areas, like coding?
They look there too. Used
Right.
benchmarks like Live Code Bench, Human Eval, plus tested models like Code R1. Same pattern emerged. Figures 4 and 5, the left parts, show it again. RLVR helps the initial success rate, sure, but the base models showed they had the potential to solve more problems if given enough shots.
Even visual reasoning, where it needs to understand images too.
Yeah, they checked that with models like Quen 2.5 VL, using benchmarks MathVista and MathVision. Figure 5, the right side, points to a similar conclusion. It doesn't seem limited to just text.
Okay, so let's get this straight. RLVR makes models more efficient, faster at finding answers it kind of already knows how to find. But what's the downside? Why does it seem to limit the overall scope?
So the paper talks about sampling efficiency. RLVR basically biases the model's output towards those paths that got rewards before, makes it more likely to spit out a correct answer quickly.
Right, like training a student only on past exam papers. They get good at those specific questions.
But maybe not great at tackling something completely new, right? The researchers argue this efficiency comes at the cost of reduced exploration capacity. Meaning, by focusing so much on those rewarded, known, good paths, the model might become less likely to explore other, potentially novel ways of thinking or solving the problem. Figure 1, the right side, tries to show this coverage decreasing as RLVR training goes on.
So it gets tunnel vision almost.
Yeah,
Really good in the tunnel, but misses what's outside.
that's a good way to put it. And they dug into why this might be happening using something called perplexity analysis.
Perplexity.
Yeah.
Sounds complicated.
Yeah. Think of it as checking if the ingredients for the reasoning paths the RLVR model uses were already available in the base model's kitchen.
Okay, so were the answers already kind of there?
They found that, yeah, these successful reasoning paths used by the RLVR models, they were already present, often with noticeable probability, in the base model's potential outputs.
Ah, so RLVR isn't creating new recipes, it's just finding and promoting the good ones that were already in the cookbook.
Exactly. It's more like highlighting and reinforcing existing patterns, not necessarily inventing whole new ways of reasoning from scratch. That feels like a really key distinction. Not expanding what it can think, just how well it accesses what it could already think.
Precisely. And this leads to an interesting comparison the paper makes with another technique, distillation.
Right, distillation. That's where you train a smaller model using the output from a bigger, smarter model, like learning from a tutor.
Exactly like that. And the researchers found that distillation, unlike RLVR, actually can introduce new knowledge and expand the reasoning boundary beyond what the base model could do alone.
Interesting.
Figure 6 on the right shows a comparison. Distillation seems to broaden the horizon in a way RLVR doesn't.
So learning from a more capable source genuinely adds new capability, whereas RLVR, based on this, seems more about refining what's already latent.
That's the implication here, yes. They also checked if maybe the specific type of RL algorithm mattered. There are different ways to implement reinforcement learning. PPO, GRPO, RLOO, REMAX, lots of acronyms.
Okay, and did they find a magic bullet? An RL algorithm that did manage to expand the reasoning? Well, there were slight differences in performance, sure. Some algorithms were a bit better than others, but the fundamental limitation, it remained. RLVR, no matter which specific flavor they tested, didn't seem to fundamentally push that reasoning boundary beyond the base model's potential. They even came up with a metric for this, the sampling efficiency gap, basically measuring how much RL helps compared to just sampling the base model a lot.
And that gap stayed big.
It stayed large across the different algorithms. Figure 7, top and table 2 lay out those results.
So fiddling with the RL method wasn't the answer.
How about it?
What about just training for longer? More RL training.
They looked at that too, the impact of RL training steps.
Yeah.
And it wasn't just more is better.
Oh.
While the initial RL training definitely improved performance on the stuff it was trained on, pushing it too far, excessive training could actually lead to diminishing returns on new data. And even worse, it could shrink that ultimate reasoning boundary, the pass at K for large K.
Wow, okay. So overtraining on the known good paths could actually make it less capable of finding novel solutions eventually.
That seems to be the finding, yeah. Figure 7, bottom, and table 3 show this trend. Too much focus might hurt exploration.
So why? Why does RLVR seem to have this ceiling when it comes to genuinely expanding reasoning? Did the paper offer reasons?
They suggested a few possibilities. One is just the sheer scale of the problem for language models.
Yeah.
The action space, all the possible words or sequences of words they could generate is astronomically huge.
Way bigger than, say, moves in chess or Go.
Infinitely bigger,
Huh.
practically. Choosing the next word, then the next from a vast vocabulary. The number of potential reasoning paths is just immense. It's hard for RL to explore that effectively, maybe.
Okay, that makes sense. What else? Another big factor is the base model itself. The pre-training gives it a really strong foundation, a strong prior about language, logic, the world.
Which is what makes it useful in the first place. Exactly. But that strong prior, while guiding it towards sensible outputs, might also act as an anchor, making it harder to explore truly novel reasoning patterns that deviate too far from what it already knows or expects.
So its own initial knowledge base might, paradoxically, limit its ability to learn fundamentally new ways of thinking via RLVR.
That's one strong possibility raised by this research. It really suggests RL might be primarily about refining the use of existing knowledge structures rather than forging completely new ones from the ground up.
Okay, let's try and summarize this for you, our listener. We've dived deep into this idea of RLVR, this reward-based training for LLMs. And while it definitely makes them better, faster at getting correct answers,
Increases that sampling efficiency.
right, this new research really challenges the idea that it's fundamentally expanding their core reasoning ability. It seems that base models, the ones without the RLVR, might already have that potential hidden inside them.
Yeah, if you just give them enough attempts, enough sampling, they can often reach or even surpass the performance of the specialized RLVR models. That's the really surprising bit.
It really is. Thinking that more compute spent just sampling the raw model could sometimes reveal more capability than spending it on further RL training.
It flips some common assumptions on their head.
Definitely. And it leaves you, the listener, with a provocative thought, right? If RLVR is mainly refining existing skills, not building totally new ones, what does that mean for the future? What kind of training or maybe even architectures will we need to get truly emergent, novel reasoning in AI?
That's the big question. It's something to chew on, maybe do some more reading about yourself.
Absolutely. Because this study really underscores that we're still figuring this stuff out. Our understanding of how these complex models learn and reason is definitely still evolving.
It's a very active, very exciting area. Lots more to discover.